how can you minimize the junction potential? So here is the entire story. Okay, so when you measure a E cell, the two electrodes, right? You're going to measure the complete E cell. So the E cell is equal to this because of the proton selective membrane, right? You are measuring the pH. So this is a reaction, this equation to describe it. So the K here has included the junction potential, which is supposed to be a constant, all the junction potentials, so that you can measure the net difference of the H plus. Okay? So the activity of the H plus in your sample solution include all the junction potential, a constant. So this is an instrument, right? Just imagine you stick your electrodes in. You want all the junction potential to be a constant, and therefore it's a K. And you only want to measure the H plus activity, okay? So this is your desirable feature. Now, how do you minimize the K? So here is the deal. That's why you need to calibrate your pH meter. Okay, so the standard, you use a pH buffer, your standard, to be approximately equal to your unknown pH. So that now you can calibrate for the junction potential. Okay, because they are of the same pH and therefore close enough to be the same constant for K. So when you put your buffer in, your E cell is equal to the same equation, right? The K plus the pH of the buffer. So now, because they are close enough, so when you stick that in, you adjust the pH meter so that the K is set for. So you have told the pH meter, this is the junction potential you're going to use. So set that fixed, okay? So fix that. So set that to that value. So you fix for the junction potential reading, okay? So this is the K. So now this K translate same K now because they are approximately equal, so you assume to be the same K. So that now you can measure the E cell by using that K. So whatever the E cell is, and you measure the pH, okay? So here is the key thing. This arrow, follow the arrow here, use the buffer to set the K, to set the junction potential. So that, okay, the P unknown versus your buffer, the difference is going to be how close your buffer to each other, okay? So the smaller difference, the better. So smaller difference, to calibrate this more accurately. So recall our exercise in the lab that if you use a pH 4 to calibrate your instrument and read pH 10 as your sample, then you read pH 10 to be 9 point something because of miscalibration for the junction potential, the K. Okay, so whenever you use a buffer solution, you standardize for the K, junction potential. Okay, any question on that? Okay, so in the real world, remember, one buffer solution is not universal for all pH. Okay. Okay, error. Now all measurements will carry errors, more or less, so you need to know limitations in any measurement. So here, when you measure the pH using the glass membrane electrode, one error source is so-called alkaline error. So alkaline, when your pH is alkaline, like pH greater than 7, then you may have this kind of error. The higher the pH, the larger this kind of error. Okay, when pH is alkaline, then that means what you have is OH minus is going to be the concentration of OH minus is going to be higher than the concentration of H plus. While your pH meter measure this activity, you measure that activity. Now, when the pH, when you have higher concentration of OH minus, then there must be coexist cations as well. So most likely, the cation will be sodium plus. Okay? So this guy is a cation, is sodium plus, and this concentration is so much higher than that concentration, and therefore, this could be mistaken by your electrode. So your electrode could measure the Na plus as if it is H plus. Even though the membrane is selective for H plus, yet when this concentration is 1,000 times higher, okay, selectivity, let's say it is 1,000 to 1, but when this is 1,000 times higher concentration, then they will be equal in terms of reading quantity, right? So this is what so-called alkaline error. Okay? So here, even though your electrode is selective for H plus, right? Then when your sodium plus concentration is high enough, then it will give a significant signal. The signal will be registered as if it is H plus. Any question on this point? Okay, then where do you get the Na plus from? Because whenever you have high concentration of OH minus, then there must be coexisting cation. What are they? Most likely will be Na plus and K plus, okay? So what you register will be too much signal, okay, mistaken is too high, and therefore the pH will be too low. So any problem seeing that? Okay, now look at the experimental outcome. So here's the plot. So here's the pH error, that much too low. So for sodium, 1 molar sodium has the largest effect. So when your pH solution is greater than 8, then it is significant because coexisting Na plus, okay, pH 9, pH 12 solution, you get a really high error here, 1 pH unit too low. Now lithium, same concentration, but different ion, then the influence can be different, So for lithium is a little lower than sodium in terms of the pH error. Then, of course, lower concentration will give you less effect. And the 2 plus, even though higher concentration than that, but because of 2 plus, your electrode is selective for single plus. So the effect from single plus is greater than from non-single plus. So any question with seeing this graph? Okay, any question?
Maybe on the test.
Well, could be, yeah. Yeah, whenever I emphasize any questions, you remember this and that, then there's a high possibility.
Makes me think that when Chuck Norris does chemistry experiments, the errors are themselves.
Okay, when when you have alkaline era, there must be acidic era. So here's the so-called acid era. Now remember, the electrode measures activity of H+. So the H+, in actuality, is carried by water, so it's hydrated. So this is the actual species in water. So you measure the activity of that. So you want each individual H+ counts in the reading, the activity. Okay, when there's a high concentration of H+, then the species, the two species or multiple species will be so close to each other. Then there will be attraction. For example, like this, between two, then you may have multiple attractions. And because of electrostatic attraction, then they end up with just one molecular ion instead of two individual, in this case, two individual ions. So it could be like this, or it could be like this. Depends on the orientation. So this could turn as just one. So your electrode is going to measure this guy as one activity, okay? But in actuality, it should be two, right? And therefore now, in terms of signal reading, then this will be read too low, okay? And therefore, the pH is too high. So any question with the low and high, because the P function? Okay, so here's a plot. That's why for pH reading, it stops at 0. pH 0, you rarely see that pH minus 0.5. So in general practice, this is something you don't have to worry about because you don't measure pH less than 1 anyway, lower than 1 anyway. But whenever it's lower than 1 or even as 0, then you get this kind of error, okay? A pH reading error would be like that for the pH less than 1. Okay, so homework, you don't need to turn in, just do this, turn this in after the exam. So the buck stops here, okay, then up for exam number 2, which is a week from today.
Up until this point of what you lectured on today,
That's right, up to here.
There's going to be one question from what you just
I
lectured.
don't know. There will be a total of 10 questions.
So, but there's
Jeffrey, try to
there's
extract.
one from today. It's going to be the electrode one.
Could be.
It is.
It's gonna be similar, 10 questions, cross time to do it, everything, yeah.
Yeah.
And you said it was a group exam, right?
You liar.
Alright, so
I have it recorded. Gotcha.
Question.
Okay.
Electrode.
So any questions?